Welcome to Thought Frontier.
Hey everyone, and welcome back for another deep dive. Today we're exploring a topic that really makes you think about how much we know about reality. The surprising connection between randomness and determinism.
It's really thought-provoking.
We've got some fascinating material to work with today, excerpts from Quantum Magazine, An American Scientist, and then a research paper all about randomness in quantum physics.
A lot to unpack.
So, where are we going with all this?
Yeah, where are we headed?
Well, by the end, you'll have a new perspective on how randomness can actually come out of systems that seem totally predictable.
Like perfectly predictable.
We'll look at this in classical mechanics, which is usually seen as the ultimate example of determinism, and then, of course, in the crazy world of quantum mechanics, where it's all about probability.
Probability rules.
And then we'll see how all of this connects to generating truly random numbers, something way more important than you might think.
More important than you might think, definitely.
Definitely. So let's kick things off with a classic example of how randomness can seem to pop up from deterministic rules. The Galton board, you know that bean machine?
Oh yeah, the bean machine.
You've got a board, rows of pegs, you drop marbles from the top. Each marble bounces around seemingly randomly
Left, right.
until it lands in one of those bins at the bottom.
Just like Plinko.
Exactly. So where's the randomness here? If you knew the exact starting position and angle of each marble, wouldn't you be able to predict its path perfectly?
Well, that's where it gets really interesting. You see, even though each individual marble's path is determined by how it hits those pegs, the overall result, the distribution of those marbles in the bins, forms a bell curve. You know, that classic bell curve.
I remember that from stats class.
So even though each marble's path is predictable, the overall outcome, it looks random.
I see, like flipping a coin. Each flip is determined by physics, but after a bunch of flips, you get about a 50-50 split. We're still in the realm of classical physics here. Does this idea of hidden determinism, does it apply to the strangeness of quantum mechanics?
Now that is a question that has puzzled physicists for a long time. You see, in quantum mechanics, even when you know everything about a system's state, the outcomes of measurements are unpredictable. It's not just that we're missing information, it's more fundamental than that the outcome doesn't exist until it's measured.
That's wild.
Think about the spin of an electron, for example. You can know its state perfectly, but when you measure the spin, the result is still random.
So the universe is like, nope, not telling you until you make me show my hand. It's like a cosmic game of poker.
This reminds me of something from the Quantum Magazine article, that even classical mechanics might have some hidden randomness. Something about a particle on a curved surface.
Oh, right. That article showed how even Newton's equations, those basic laws of classical physics, sometimes can have multiple solutions.
Multiple solution, which means that the future motion of a particle can become unpredictable. It challenges the idea that classical mechanics is always completely deterministic.
So even in this supposedly predictable world of classical physics, there could be randomness hiding underneath.
Right. This isn't a new idea either. A physicist named Boussinesq, way back in the 19th century, suggested that maybe classical mechanics isn't the whole story, that it needs more laws to explain these random-looking situations.
So maybe there are hidden variables at play, just like in that Galton board example.
Exactly, influencing the outcome. But how does this connect to the craziness of quantum mechanics? That's where things get really bizarre, right?
Yeah.
Absolutely. Quantum mechanics has this built-in randomness. It's even deeper than in classical physics. A key concept here is contextuality.
The contextuality.
It's illustrated by something called the Koch-Specker theorem.
Okay, now you're just using big words to scare me.
No, it's actually pretty straightforward. The theorem basically says that the outcome of a quantum measurement, it depends on how you measure it. It's not just that we don't know enough. It's like the act of measuring is messing with the system.
Okay, that's weird. But if we can't predict outcomes in quantum mechanics, how do we know it's truly random? What if there's some deeper level of reality, some rules we haven't found yet that are actually deciding everything?
That's where another mind-bending concept comes in. Non-locality. Imagine two particles that are entangled, separated by a huge distance. If you measure one, it instantly affects the other, no matter how far apart they are.
Wait, so if I flip a coin here and my friend flips one on the other side of the world and they both land on heads, that's non-locality.
Not quite. It's even weirder than that. It challenges a fundamental idea in classical physics that things can't influence each other faster than light. Einstein called it spooky action at a distance.
Spooky action at a distance. I like that. He thought there must be some hidden variables that we're missing.
Right, some predetermined plan. But then came Bell's theorem. It showed that if we assume that information can't travel faster than light, the outcomes of these quantum measurements have to be truly random, not just because we don't know enough.
So Bell's theorem basically says, sorry, Einstein, no hidden variables here. The randomness we see isn't a bug, it's a feature. That's incredible. But with all this talk about randomness, what does it mean for us, for the real world?
Well, this is where we get to one of the most practical applications of quantum randomness, making truly random numbers.
Oh, random numbers. I use those all the time in my spreadsheets.
Well, those random number generators on computers, they might seem random, but they actually use algorithms. They're not truly unpredictable.
So they're not actually random.
Nope. Quantum randomness is the real deal. Quantum random number generators, we call them QRNGs, they use the inherent randomness of quantum measurements to make totally unpredictable sequences of numbers.
So like a machine that just spits out random numbers using quantum mechanics, how does that even work?
There are a few ways to do it. Some systems use the randomness of detecting single photons. Others use the randomness of laser light.
So we've got this incredible resource in quantum mechanics, a way to generate truly random numbers. What can we actually do with that?
Oh, it's huge. One of the most important applications is in cryptography.
Cryptography?
Yeah, keeping communication secure. With truly random keys for encryption, it becomes really, really hard for hackers to break in.
Oh, wow, like unbreakable codes. And what about other applications?
They're everywhere. Scientific research relies on unpredictable simulations. Anywhere you need something truly random, QRNGs can provide it.
But we read that even with these quantum processes, making sure the random numbers are high quality isn't easy, right?
Yeah, you're right. That research paper we mentioned, it goes into how even with quantum mechanics doing the heavy lifting, you still need techniques to extract randomness and make sure the numbers are top-notch.
So it's more complicated than just pointing a laser and getting random numbers?
Exactly. There's a whole science to making sure the randomness is truly high quality. It's like refining oil to get pure gasoline. But where does this all lead? What's the next big thing in quantum randomness? Well, that brings us to the world of something called device-independent quantum information processing.
Device-independent? What's that all about?
It's about making sure things are secure even if the devices you're using aren't trustworthy, or even if they might be manipulated.
That sounds important, especially with all the cybersecurity concerns these days. But how can you do that? If you can't trust the devices, how can you be sure of anything?
That's where Bell non-locality comes in. It lets us make sure the randomness is genuine, even if we don't know everything about the devices being used. It's like checking if a diamond is real without knowing where it was mined or how it was cut.
That's amazing. But how do you actually quantify randomness in the real world? Like, how do you measure it?
Good question. We need to figure out how much entropy a system has, which is basically a measure of randomness that's essential for those randomness extraction techniques to work properly. And then there's the issue of noise. You know, those pesky real-world imperfections that can mess things up. The research paper talks about how even with lasers, you have to deal with thermal and technical noise.
So it's a balancing act between harnessing the power of quantum randomness and dealing with the messiness of reality.
Exactly. This field is moving fast. There's so many possibilities. But there are definitely some big challenges ahead, too.
This is all so fascinating. I'm curious to hear more about what's next in this quantum randomness revolution.
Let's dive into that next time.
So much to think about. It's amazing how much potential there is in this field.
Absolutely. And, you know, what's really incredible is that these techniques don't just generate randomness. They actually prove it's really random. That's where those Bell inequalities we talked about come in. By violating these inequalities, we can be certain that the randomness we're creating is truly unpredictable, even for someone with, like, a supercomputer.
So it's like having a certificate of authenticity for your randomness. That's a game changer for things like cryptography, where trust and security are so important.
Exactly. It's like a lock with a key that's been made by the universe itself, with all its randomness built in.
I love that analogy. It makes me think about something we touched on earlier, free will. Does all this randomness in quantum mechanics mean that the universe is fundamentally unpredictable? Like, is there no such thing as cause and effect?
Now you're getting into the deep philosophical questions, the kind of stuff people have been debating forever. And the answer, just like a lot of things in quantum mechanics, isn't so simple. On the one hand, Bell's theorem tells us that there aren't any hidden variables pulling the strings behind the scenes. The randomness we see isn't just because we don't know enough. It's baked into the universe.
So at the quantum level, things really do happen by chance. Does that mean our lives are just a bunch of random events? Does that mean free will is just an illusion?
Hold on, hold on. Not so fast. We have to remember that quantum mechanics mostly governs the microscopic world, the tiny stuff. How this randomness affects the world we experience, the macroscopic world, is still a mystery.
Okay, so it's more complicated than that.
Much more. Some physicists think this randomness might average out on larger scales, leading back to that deterministic behavior we see in classical physics.
So the randomness kind of disappears as you zoom out?
In a way. But other physicists think that quantum randomness might play a bigger role in shaping reality than we realize.
So there's still a lot we don't know about how it all fits together. It's kind of humbling in a way.
It is, but even if we can't answer all the big philosophical questions right now, just the fact that we can use this quantum randomness for practical stuff is amazing in itself.
That's true. Okay, so we've talked a lot about the theory. What about actually building these quantum random number generators? What are the nuts and bolts of making them work?
That's where the engineers come in. As we mentioned before, there are different kinds of QRNGs, each with its own advantages and disadvantages. You have your single photon systems. Those are based on the randomness of when individual photons hit a detector. They're simple in theory, but can be slow. And then there are continuous variable systems, like those that use laser light. They're much faster, but they need careful calibration to make sure the randomness is high quality.
So it's like a trade-off between speed and complexity. What do scientists have to consider when they're designing these things?
Lots of things. One key factor is the source of the randomness. Some systems use radioactive decay, others use the fluctuations in light, still others use the behavior of trapped atoms. Then there's the detection method. How do you actually measure these quantum events and translate them into a stream of random numbers?
Sounds complicated. Are there any examples of these QRNGs out in the real world?
Oh yeah, they're already being used. Some companies are building QRNGs into cybersecurity products to make encryption keys. Researchers are using them for experiments and simulations where high-quality randomness is crucial.
Wow, so it's not just a theory anymore. Are these things expensive? Will I ever have one in my phone?
That's a good question. Right now, they're still pretty specialized and not cheap. But as the technology gets better and more people need them, I think the cost will come down. There are even projects working on miniature QRNGs that could be put into everyday devices.
That's amazing. Okay, let's shift gears for a minute and go back to some of those big philosophical questions. We talked about free will, but quantum randomness raises all sorts of other interesting questions, right?
It sure does. One of the most mind-blowing questions is what it tells us about cause and effect. In classical physics, it's all about a straight line from cause to effect. But in quantum mechanics, it's not so clear.
So you're saying that in quantum mechanics, things don't always happen for a reason?
Not exactly. It's more like the outcomes of quantum events aren't set in stone beforehand. They come out of a bunch of different possibilities.
So does that mean the universe is just random at its core? No rhyme or reason to anything? That's a little unsettling, to be honest.
It can be tough to wrap your head around. But you have to remember that randomness doesn't always mean chaos or meaninglessness. Some physicists think this quantum randomness might be what allows for creativity, for new things to happen, maybe even for free will. After all, if everything was predetermined, there wouldn't be any room for choice, right?
Yeah, that's a good point. Maybe randomness is what makes the universe dynamic, what allows it to evolve and change.
Right, it's what keeps things interesting.
But if we can't predict the future, does that mean science is pointless? Like, what's the point of trying to understand the universe if it's all just random?
Not at all. Science is all about finding the patterns and regularities that come out of randomness. Even in a world where individual events are unpredictable, we can still build theories and models that explain how things behave on average.
So science isn't about getting rid of randomness. It's about understanding it, about finding the order within the chaos. That's actually kind of comforting. But what does this all mean for us? For our place in the universe? If we're not just cogs in a deterministic machine, then what are we?
Those are the questions that philosophers and theologians have been asking for centuries. And they're even more relevant now that we have quantum mechanics. The exciting thing is that we're finally starting to have the tools to explore these questions in new ways.
I agree. It feels like we're at the beginning of a whole new era of understanding. It's amazing how something as complex as quantum mechanics can make us question some of the most basic things about reality.
It is. This whole deep dive's been a wild ride, and I feel like we're just scratching the surface.
Me too. And you know, The American Scientist article we talked about goes even deeper into how scientists are trying to use these quantum principles to create a source of unlimited random numbers.
Unlimited. Now, that's something I have to hear more about.
Right. It sounds like something out of science fiction.
It does, doesn't it?
Yeah.
The article talks about something called infinite randomness expansion. And you guessed it, it relies on those spooky, non-local correlations that we've been discussing.
Okay, I'm officially intrigued. Infinite randomness. How is that even possible?
Well, think of it like this. You start with a small amount of truly random bits, like a tiny seed. And then you use that seed to create an endless stream of random numbers, like a fountain of randomness that never runs dry.
Okay, you officially blew my mind. But as cool as that sounds, I'm guessing there are some big challenges in actually making this work, right?
Oh, definitely. According to the article, one of the biggest hurdles is speed. We need to figure out how to generate these random numbers way faster if we want them to be useful for real-world stuff.
I can see that. For things like high-speed trading or encrypting data on the fly, speed is everything.
Exactly. And then there's the issue of security. When you're talking about a potential source of unlimited randomness, you have to be absolutely sure it's protected from anyone trying to mess with it or predict what's coming next.
So it's not enough to just create randomness. You have to guarantee that it's truly unpredictable and can't be tampered with.
Exactly. And that's a whole other level of difficulty when you're dealing with quantum systems. It's like trying to protect a system that's based on rules of a universe we're just starting to understand.
It sounds incredibly challenging, but also incredibly exciting. Imagine the possibilities if we could pull this off. It would be like having a universe of random numbers at our fingertips.
It's mind-blowing, isn't it?
Yeah.
We could have encryption that's impossible to break, simulations that are so realistic they're almost indistinguishable from reality, maybe even new forms of art and music based on pure randomness.
It's almost too much to comprehend. It makes you wonder what other incredible things might be hidden within the fabric of reality, just waiting to be discovered.
Absolutely. This whole deep dive has really driven home the point that the universe is far stranger and more amazing than we often give it credit for. And it's that pursuit of knowledge, that drive to push the boundaries of what we know, that makes life so fascinating.
I couldn't agree more. I feel like we've covered so much ground today, from the surprising randomness in classical physics to the incredible world of quantum mechanics and the potential for unlimited randomness. But I think what strikes me the most is the sheer sense of wonder and awe that this topic inspires.
I think that's a perfect takeaway. We've gone deep into some complex ideas, but ultimately this exploration is about fostering a deeper appreciation for the mysteries of the universe and how we fit into it all.
Well said. To our listeners, we hope you've enjoyed this deep dive into the world of randomness and determinism. We encourage you to keep exploring these ideas, to question, to wonder, and to never stop learning. After all, as we've discovered today, the most unexpected places often hold the most profound insights. And who knows what amazing discoveries are waiting for us just around the corner.
I completely agree. And remember, the next time you flip a coin or gaze up at the stars, take a moment to consider that delicate dance between chance and order that shapes our universe.
What a beautiful thought to end on. Thanks for joining us on this incredible journey, everyone.